Hello, everyone. In this video, we are going to discuss surfaces in space such as constant surfaces, cylindrical surfaces, and surfaces of revolution. Surfaces in space. In a previous video, we discussed planes. A plane in space is characterized by a point in the plane and a normal vector. That is orthogonal to a vector formed from the point in the plane to another point in the plane. The point provides the location at which the plane is required to pass through, while the normal vector provides the orientation of the plane in space. The dot product of two orthogonal vectors is equal to 0, so the dot product of the normal vector and the vector on the plane is equal to 0. Thus, the standard form of the equation of the plane is given by the following equation. Meanwhile, the general form of the equation of a plane is this equation that is at most linear in each variable. The standard form can be written in general form by distributing the coefficients and combining like terms. Sphere. A sphere is a surface that consists of all points that are equidistant to the center. It has circular horizontal and vertical traces. The standard form of the equation of a sphere that has a radius r and centered at the origin is given by the following second-degree equation. If the sphere is centered at point H, K, L, this is the standard form of the equation. When written in standard form, all quadratic terms on one side are positive, and the constant term on the other side is also positive. The equation of a sphere can also be written in general form. It has quadratic terms in each variable. The linear terms and the constant term may or may not appear depending on the center of the sphere. Constant surfaces. A constant surface consists of all points that are characterized by a constant measurement. First, let us look at constant surfaces in rectangular coordinates. When a point is written in rectangular coordinates, the first number is the x-coordinate, and it is the distance of the point from the yz plane. The second number is the y-coordinate, and it is the distance of the point from the xz plane. And the third number is the z-coordinate, and it is the distance of the point from the xy plane. So it follows that a constant surface in rectangular coordinates is a surface that consists of all points that have a constant distance from a coordinate plane. The graph of x equals a constant x0 is a vertical plane, whose distance from the yz plane is x0. The graph of y equals a constant y0 is a vertical plane, whose distance from the xz plane is y0. The graph of z equals a constant z0 is a horizontal plane, whose distance from the xy plane is z0. Next, let us study constant surfaces in cylindrical coordinates. When a point is written in cylindrical coordinates, the first number is the r-coordinate, and it is the distance of the point from the z-axis. The second number is the theta-coordinate, and it is the angle that the point makes with the positive x-axis. And the third number is the z-coordinate, and it is the distance of the point from the xy plane. So it follows that constant surfaces in cylindrical coordinates have the following graphs. The graph of r equals a constant r0 is a right circular cylindrical surface centered on the z-axis, with radius r0. The graph of theta equals a constant theta0 is a half-plane that starts along the z-axis, and makes an angle of theta 0 with the positive x-axis. The graph of z equals a constant z0 is a horizontal plane, whose distance from the xy plane is z0. Finally, let us find out constant surfaces in spherical coordinates. When a point is written in spherical coordinates, the first number is the rho-coordinate, and it is the distance of the point from the origin. The second number is the theta-coordinate, and it is the angle that the point makes with the positive x-axis. And the third number is the phi-coordinate, and it is the angle that the point makes with the positive z-axis. So it follows that constant surfaces in spherical coordinates have the following graphs. The graph of ρ equals a constant ρ0 is a sphere centered at the origin, with radius ρ0. The graph of theta equals a constant theta 0 is a half-plane that starts at the z-axis, and makes an angle of theta 0 with the positive x-axis. The graph of phi equals a constant phi 0 is a right circular cone with vertex at the origin, whose surface makes an angle of phi 0 with the positive z-axis. Cylindrical surfaces. These are graphs of equations containing only two of the variables x, y, and z. A cylindrical surface is characterized by the plane curve lying on the corresponding coordinate plane of the two variables, and the rulings which are lines parallel to the axis of the remaining variable. The cylindrical surface on the left has an equation of an ellipse in variables x and y. Hence, the rulings are parallel to the z-axis. Meanwhile, the cylindrical surface on the right has an equation of a parabola in variables y and z. Thus, the rulings are parallel to the x-axis. Surfaces of revolution. These are surfaces generated when a curve is rotated about a coordinate axis. Revolution about the x-axis. The equation has the sum of y squared and z squared, and it is equal to the square of the radius function of x. As an example, for a line r of x equals x on the xy or xz plane, Revolve the curve around the x-axis to generate the surface. The equation of the surface of revolution about the x-axis is the following equation. The surface has circular traces perpendicular to the x-axis. The radius of a circular trace left by a vertical plane on the surface depends on x, which means the radius of the surface changes along the x-axis. Revolution about the y-axis. The equation has the sum of x squared and z squared, and it is equal to the square of the radius function of y. For a square root trace r of y equals the square root of y on the xy or yz plane. Revolve the curve around the y-axis to generate the surface. The equation of the surface of revolution about the y-axis is the following equation. The surface has circular traces perpendicular to the y-axis. The radius of a circular trace left by a vertical plane on the surface depends on y, which means the radius of the surface changes along the y-axis. Revolution about the z-axis. The equation has the sum of x squared and y squared, and it is equal to the square of the radius function in z. For a half-circle trace r of z equals the square root of quantity r squared minus z squared on the xz or yz plane. Revolve the curve around the z-axis to generate the surface. The equation of the surface of revolution about the z-axis is the following equation. The surface has circular traces perpendicular to the z-axis. The radius of a circular trace left by a horizontal plane on the surface depends on z, which means the radius of the surface changes along the z-axis. Quadric surfaces. The graph of a second-degree equation in three variables x, y, and z is a quadric surface. There are 6 types of quadric surfaces: ellipsoid, hyperboloid of one sheet, hyperboloid of 2 sheets, elliptic cone, elliptic paraboloid, and hyperbolic paraboloid. The equations of quadric surfaces have all the 3 variables x, y, and z. The equations differ on the sign of the quadratic terms. The value of the constant term, and whether it is linear in one variable. These equations are for quadric surfaces centered at the origin. An equation changes when there is rotation about an axis, translation of the center to another point, and a change in the orientation of the quadric surface. For instance, for an elliptic paraboloid centered at the point h, k, l, that opens to the positive y direction, the equation becomes the general form of the equation of a quadric surface is given by the following equation. There are quadratic terms in one variable, quadratic terms in two variables, linear terms, and a constant. The quadratic terms in two variables appear when the quadric surface has rotation about an axis. The linear terms appear when the quadric surface has translation of center or vertex from the origin. The standard form of the equation of a quadric surface can take one of these forms. A quadric equation in general form can be converted into a standard form by completing the squares of each polynomial in one variable, and then dividing the whole equation by a number that makes the equation become a standard form. In this form, the type of quadric surface can be identified easily using the signs of each term. Moreover, the center or vertex can also be determined by inspection. Traces. A trace is the intersection of a surface and a plane. Consider a surface in 3D space. A horizontal trace is left by a horizontal plane z equals z0, where z0 is a constant. Horizontal traces are parallel to the xy plane. A vertical trace is left by a vertical plane y equals y0, where y0 is a constant. These vertical traces are parallel to the xz plane. Or a vertical plane x equals x0, where x0 is a constant. These vertical traces are parallel to the yz plane. To find the equation of a trace, first, substitute the constant that corresponds to the cutting plane into the equation of the surface. For the surface with the following equation, the equation of the trace left by a horizontal plane z equals z0 is this pair of equations. A trace is an equation in two variables, and it is accompanied by the equation of the plane that made the trace. If the equation of the plane is not specified, by default, an equation in two variables would refer to the equation of a cylindrical surface. Second, rewrite the equation in general form or standard form, if needed. Please watch the next video for a discussion about the types of quadric surfaces. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.